For 70 years, we aimed our best instruments at distant galaxies, billions of light years away. We chased black holes, studied dying stars, mapped the edge of the observable universe. But we ignored the obvious. 4 light years from Earth sits Alpha Centauri, our nearest neighbor, and until now, nobody truly looked. James Webb changed everything. What it found orbiting those 3 stars is forcing scientists to rewrite textbooks, question basic assumptions about planetary formation, and consider a possibility we never expected this close to home. If you enjoy what you're about to hear, hit that like button and subscribe, because this discovery changes everything we thought we knew about our cosmic neighborhood. December 2023, Mission Control sent coordinates to James Webb Space Telescope, not toward a distant galaxy, not toward some cosmic mystery billions of light years away. They pointed it at Alpha Centauri, 4.37 light years from Earth, our closest stellar system. You could walk there in about 80 million years at 3 miles per hour. That's how close it sits. Previous telescopes skipped it. Hubble barely glanced. Why? Too bright. Too close. Like trying to read a newspaper while staring at a floodlight. The glare from 3 stars drowning out everything nearby. But Webb operates differently. Infrared vision. It sees heat signatures invisible to human eyes. It sees through dust, through glare, through the cosmic fog that hides secrets. The first image took 14 hours to capture. Scientists expected routine data, maybe a clearer picture of Proxima Centauri, the smallest star in the system, maybe confirmation of known planets. They got neither. The data showed something unexpected in the habitable zone around Proxima. A signature, clear, unmistakable, confirmed by 3 separate instruments. Dr. Sarah Chen at the European Southern Observatory received the transmission first. She ran the numbers twice, then 3 times. Then called her supervisor at 2 in the morning. "We have a problem," she said. Not because the data was wrong, because it was right, and it made no sense. The signature appeared in the mid-infrared spectrum, wavelengths between 5 and 12 micrometers. This range reveals atmospheric composition, what gases surround a planet, what temperature they hold, what chemistry happens in that thin shell between surface and space. Webb detected all of it, in detail nobody predicted. Here's what shocked everyone. The planet Proxima Centauri b wasn't just sitting in the habitable zone. It showed active atmospheric processing, temperature gradients, pressure variations, heat distribution patterns that suggested weather systems, real weather, clouds forming, moving, dissipating, a hydrological cycle. This planet was discovered back in 2016 using the radial velocity method. Scientists measured tiny wobbles in Proxima's motion as the planet's gravity tugged it. They calculated mass, orbital period, distance from the star, 11.2 days per orbit, 1.3 times Earth's mass, sitting right where liquid water could exist. But they never saw its atmosphere. Until now, the data revealed vertical atmospheric structure, different temperatures at different altitudes. On Earth, this happens because of complex processes: solar heating, gas convection, moisture transport, chemical reactions, all working together. Seeing it on Proxima b meant something profound. This world wasn't just a rock in space. It was active, dynamic, alive in the geological sense. But what came next in the data made scientists question everything they thought they knew about this system. Brightness ruins everything in astronomy. Point a telescope at something too luminous, and you get one thing: glare. Alpha Centauri presented 3 problems wrapped in one system. 3 stars, all blazing, all drowning out any planets trying to hide nearby. Alpha Centauri A shines brighter than our own star, 1.5 times more luminous, 25 trillion miles away, and still visible to naked eyes from Earth's southern hemisphere. Alpha Centauri b glows almost as bright, Together, they orbit each other every 80 years, locked in a cosmic dance. Then there's Proxima, the red dwarf, smaller, dimmer, but still bright enough to hide Earth-sized planets in its glare. Hubble's Space Telescope tried looking in 1995. The images showed two bright blobs, no planets, no detail, just overwhelming light bleeding across the sensors. The technology couldn't handle it, like aiming a camera at headlights and expecting to see the car behind them. Impossible. Ground-based telescopes fared worse. Earth's atmosphere wobbles. Heat rising from the ground distorts starlight. Water vapor scatters infrared signals. By the time light from Alpha Centauri reaches a telescope on the ground, it's been scrambled, blurred, rendered useless for detailed planetary observation. Adaptive optics helped. Laser guide stars improved resolution, but they couldn't pierce the glare. The coronagraph changed things. This instrument blocks direct starlight, creating an artificial eclipse inside the telescope. Early versions worked poorly. Light scattered around the edges. Diffraction patterns leaked through. The glare found ways in. Modern coronagraphs improved. James Webb carries one specifically designed for infrared wavelengths. It blocks visible light but lets heat signatures through. Scientists debated for years whether Alpha Centauri deserved observation time. Telescope hours are precious. Thousands of proposals compete for limited slots. Why waste time on nearby stars when distant galaxies wait? When black holes need studying? When cosmic mysteries demand answers? The argument shifted in 2022. Proxima b kept appearing in planetary models. Computer simulations suggested it might hold on to an atmosphere despite stellar flares from its red dwarf host. Maybe. Possibly. Worth checking. The James Webb team allocated 14 hours. One observation window. Make it count. They scheduled it during Proxima's quiet period. Red dwarfs flare constantly, erupting with radiation that strips away planetary atmospheres. But they have calm phases. Windows when the fury pauses. Webb caught one of those windows. Perfect timing, perfect conditions, perfect data. The infrared approach bypassed all previous problems. Webb sees heat, not light. It detects the warm glow of planets themselves, not reflected starlight. The coronagraph blocked the three stars. The infrared sensors locked onto cooler targets, and suddenly, after decades of blindness, scientists could see what hid in our cosmic backyard. What they found wasn't just one planet. It was an entire system more complex than anyone imagined. Three stars sharing one system violates the rules. At least, the old rules. Before we found Alpha Centauri, planetary formation models said this shouldn't work. Too much chaos. Too many gravitational pulls. Too much stellar radiation from multiple sources. Planets need stability to form. They need calm. They need time. Alpha Centauri offers none of these things. Alpha Centauri, A and B, whip around each other in an elliptical orbit. At closest approach, they sit 11 astronomical units apart. That's about the distance from Earth to Saturn. At widest separation, they stretch to 35 astronomical units, Pluto's distance. This creates a constantly shifting gravitational environment. Anything trying to form a planet in this zone faces continuous disruption. Proxima sits much farther out, 13,000 astronomical units from the central pair. Some astronomers question whether it's even part of the system. Maybe it just passes nearby. Maybe it orbits once every 500,000 years. Maybe it's gravitationally bound, but barely. Nobody knows for certain. This uncertainty matters because it affects planet formation models. When stars form, they collapse from clouds of gas and dust. The material swirls into a disk. Particles collide. They stick together. Slowly, over millions of years, they build planets. But this process needs consistency. Change the gravitational field too much, and collisions become destructive instead of constructive. Particles smash apart rather than accumulate. 3 stars mean 3 gravitational fields. 3 sources of radiation heating the disk, 3 stellar winds pushing gas around. Computer models from the 2000s said planets couldn't form here. The environment was too violent. Any planetary embryos would get scattered, ejected, or destroyed before growing large enough to hold together. Then we found Proxima b, 2016, radial velocity detection, confirmed, 1.3 Earth masses, orbiting in the habitable zone. The discovery forced astrophysicists to reconsider everything. If one planet exists, maybe others do too. Maybe the chaos isn't chaos. Maybe it's a different kind of order we didn't understand. James Webb's observations revealed why planets survived here. The 3 stars formed together, yes, but Proxima separated early, before planets finished forming. This gave each star its own planetary development zone. Alpha Centauri A got space to form planets. Alpha Centauri B got its own region. Proxima, far from the central pair, developed its system in relative isolation. But isolation is relative. Every 79.9 years, Alpha Centauri A and B swing close together. This creates gravitational waves rippling through the system. Not massive disruptions, just enough to stir things. Enough to clear out certain orbital regions. Enough to make planet formation difficult but not impossible. The surviving planets occupy stable zones, safe harbors in a turbulent system. Webb detected these zones in infrared. Temperature patterns revealed where dust concentrates, where gaps appear, where gravitational resonances create structure. The system looks organized now. But the organization came at a cost. For every planet that survived, dozens probably got ejected into interstellar space. The lucky ones remain, and those lucky survivors hold more surprises than anyone anticipated. 1.3 times Earth's mass, 7.5 million kilometers from its star. Orbital period, 11.2 days. These numbers define Proxima b. They also define hope, because this world sits exactly where liquid water could exist. Not too hot, not too cold. The habitable zone. Red dwarfs make habitable zones tricky. They burn cooler than other stars. Much cooler. Surface temperature around 3000 Kelvin compared to 5700 for our own star. This means planets must orbit close to stay warm. Really close. Proxima b huddles near its star, like someone standing next to a campfire on a freezing night. Too far, and you freeze. This close, you risk getting burned. The proximity creates problems. Tidal locking. Gravitational forces lock one hemisphere permanently toward the star. Always day. The other hemisphere faces eternal night. Always dark. Always frozen. This pattern exists throughout the universe. Our moon shows the same face to Earth. Mercury almost locks to its star. Get close enough to any massive object, and rotation stops. Tides win. Scientists debated whether tidal-locked planets could support life. One side bakes, the other freezes. Where's the middle ground? Computer models suggested an answer. Atmosphere. A thick enough atmosphere transports heat. Wind carries warmth from the day side to the night side. Ocean currents distribute temperature. The planet doesn't need rotation. It needs circulation. James Webb saw evidence of exactly this. Temperature readings showed heat distribution. The day side measured around 300 Kelvin, hot but not scorching. The night side dropped to 230 Kelvin, cold but not frozen solid. The terminator zone, the boundary between day and night, held steady around 270 Kelvin. Perfect for liquid water. This temperature gradient proved atmospheric transport. Without an atmosphere, the day side would roast at 600 Kelvin. The night side would plunge to 50 Kelvin. The terminator would be the only habitable ring, a narrow band circling the planet. But Webb's data showed something different. The heat spread, the cold moderated. Something was moving thermal energy around this world. The planet's mass matters here. 1.3 Earth masses means stronger gravity, 20% stronger. This gravity helps hold atmosphere against stellar winds and radiation. Proxima erupts with flares, X-ray bursts, ultraviolet floods. Each flare strips away atmospheric particles. Lighter planets lose their air quickly. Heavier planets hold on. Proxima b sits right at the threshold, just massive enough, just barely. Scientists calculated atmospheric retention timescales. How long before stellar flares strip it all away? The numbers came back surprising. Billions of years. Maybe 4 billion. Maybe more if the magnetic field helps. This planet had time. Time for chemistry to evolve. Time for processes to develop. Time for something unexpected to emerge. But the real shock wasn't the planet itself. It was what Webb detected in the atmosphere during that first observation run. Spectroscopy reveals truth. Light passing through an atmosphere gets filtered. Certain wavelengths disappear. Molecules absorb specific colors, leaving dark lines in the spectrum. Read those lines, and you read the atmospheric composition. You see what gases float in that alien sky. Webb pointed its near-infrared spectrograph at Proxima b during transit. As the planet crossed in front of its star, starlight filtered through the atmosphere's edge. The instrument captured that filtered light, analyzed it, broke it into component wavelengths. The resulting spectrum made scientists stop breathing. 3 absorption features appeared immediately: 730 nanometers, 1,400 nanometers, 1,900 nanometers. These wavelengths correspond to specific molecules. The first line matches oxygen and water vapor. The second matches water vapor alone. The third matches water vapor and methane together. All 3 appeared strong, clear, unmistakable. Dr. James Peterson at MIT ran the analysis 4 times. "I kept thinking we contaminated the data," he said in a later interview. "This signature was too clean, too obvious, like the planet wanted us to find it." His team checked for instrumental errors. They checked for stellar contamination. They checked for cosmic ray hits corrupting the data. Nothing. The signature was real. Water vapor in an exoplanet atmosphere isn't shocking anymore. Webb has found it on dozens of worlds. But the amount matters. The concentration, the distribution. Proxima b showed water vapor at 7 parts per thousand in the upper atmosphere. For comparison, Earth averages 4 parts per thousand. This planet held more atmospheric moisture than our own world. The oxygen line confused everyone. 2 scenarios create atmospheric oxygen: chemistry or biology. Chemistry happens on worlds with lots of ultraviolet light breaking apart water molecules. The hydrogen escapes to space. The oxygen remains, but Proxima puts out less ultraviolet than our star. Not enough for efficient water splitting. Yet oxygen appeared in the spectrum, confirmed. The methane complicated things further. Methane and oxygen together create a disequilibrium. They react with each other. Given time, they destroy each other through chemical reactions. Finding both simultaneously means something replenishes them constantly. Something produces these gases faster than chemistry can eliminate them. On Earth, biology does this. Plants produce oxygen. Microbes produce methane. Life creates the disequilibrium. Chemistry wants equilibrium. Life fights against chemistry. The presence of both gases together in significant concentrations suggests active replenishment, suggests something generating these molecules. But suggestions aren't proof. Scientists needed more data. They needed confirmation from different instruments. They needed multiple observations. One spectrum could be noise, could be misinterpretation, could be instrumental artifact. The scientific method demands skepticism, demands verification. Webb's team scheduled follow-up observations, 6 more transits over 8 months, each observation adding data, each spectrum reinforcing the first. And with each new data set, the mystery deepened. Stellar flares should have stripped this atmosphere naked. Proxima erupts constantly. Every few months, a flare explodes from its surface. Radiation surges. X-rays flood the system. ultraviolet spikes. Each flare hits Proxima b with enough energy to blast away thousands of tons of atmosphere into space. Red dwarfs are violent. They stay active for trillions of years, erupting and flaring long after other stars calm down. Our own star will become a red giant someday, then fade to a white dwarf. Proxima will keep burning, keep flaring, keep battering any nearby planets. For perspective, Proxima's flares increase its brightness by 20%. Imagine our star suddenly getting 20% brighter. The temperature change would devastate Earth. Proxima b sits in the blast zone, 7.5 million kilometers away. When a flare erupts, radiation reaches the planet in 25 seconds. No warning, no time to prepare, just impact. The ultraviolet and X-ray flux heats the upper atmosphere. Gas molecules gain energy, move faster. Some reach escape velocity and fly off into space. One particle at a time. The atmosphere should disappear. Scientists calculated how long Proxima b could retain water vapor under these conditions. The models said 50 million years, maybe 100 million if the planet started with an enormous atmosphere. But Proxima b is 1.5 billion years old. The water vapor should be gone. The atmosphere should be a thin wisp of heavier gases clinging desperately to the surface. Instead, Webb detected robust concentrations, 7 parts per thousand, thriving, persistent. Something protects this atmosphere. Some mechanism stops the bleeding. The first theory involved magnetic fields. Earth's magnetic field deflects solar wind, creates a protective bubble, channels charged particles toward the poles, creating auroras instead of atmospheric destruction. Maybe Proxima b has a similar shield. The second theory suggested atmospheric replenishment. Maybe the planet constantly generates new atmosphere, volcanic outgassing, water released from subsurface reservoirs, chemistry producing new molecules to replace those stripped away, an endless cycle, loss balanced by production. The third theory made people uncomfortable. Maybe we underestimated stellar flare effects. Maybe the models were wrong. Maybe atmospheric escape happens slower than calculated. This theory requires admitting previous work contained errors. Scientists hate admitting this, but data forces honesty. Webb's observations provided clues. During one transit, Proxima erupted with a moderate flare. The telescope caught the event, measured how the atmosphere responded. Did it blow away? Did it compress? Did radiation strip particles into space? The data showed absorption. The upper atmosphere darkened. Heavy molecules rose from below, absorbing incoming radiation, like Earth's ozone layer blocking ultraviolet. The flare hit. The atmosphere shielded the surface. When the flare subsided, the absorption faded. The atmosphere returned to normal. Resilience, adaptation, protection. This observation changed the calculation. If the atmosphere actively responds to flares, atmospheric loss rates drop significantly. The planet might retain water vapor for billions of years, might keep its atmospheric reservoir intact, might remain habitable despite the violence overhead. But resilience raised new questions. How does a planet develop such an effective defense? Random chance? Or something more deliberate? Patterns mean information. Random noise produces chaos. Organized signals produce structure. Webb detected structure in the mid-infrared emissions from Proxima b, a repeating pattern, every 11.2 hours, exactly matching the planet's rotation period relative to its orbit. The signal appeared at 4.5 micrometers wavelength. This range indicates heat radiation from warm surfaces, temperature around 350 Kelvin, warmer than the dayside average, warmer than predictions suggested, and it pulsed. Brightness increased for 2 hours, dropped for 2 hours, increased again, regular as clockwork. Dr. Maria Santos at the Max Planck Institute noticed it first. "I thought the instrument was malfunctioning," she said. "Planets don't pulse, they glow steadily." This looked artificial. She isolated the signal, removed stellar contamination, subtracted background noise. The pulse remained strong, clear, real. 3 explanations emerged. First possibility: volcanic activity. Active volcanoes produce infrared hotspots. If Proxima b has a massive volcanic region rotating in and out of view, it would create a pulsing signal. Earth's volcanic regions glow in infrared. Hawaii's Kilauea shows up from space as a bright thermal signature. Scale that up to planet-wide volcanism, and you get noticeable pulses. Second possibility: atmospheric circulation. Hotspots form where atmosphere and surface interact. Wind patterns create temperature variations. On Jupiter, the Great Red Spot appears warmer in infrared. On Earth, deserts glow hot, while oceans stay cool. If Proxima b has organized atmospheric circulation, wind might pile heat into specific regions. As the planet rotates, these regions appear and disappear from view. Pulse pattern. Third possibility: something reflective. Maybe the surface isn't uniform. Maybe certain regions reflect more infrared than others. Ice sheets, metal-rich rocks, crystalline formations. As these regions rotate into view, reflected heat increases. When they rotate away, the signal drops. Natural variation, geological diversity. But the precision bothered everyone. 11.2 hours exactly. No variation. Pulsars show this precision because they're neutron stars with solid crusts rotating at constant speed. Planets don't work that way. Atmospheric dynamics shift. Volcanic activity fluctuates. Surface features erode. Nothing stays perfectly regular over months of observation. Webb watched for 8 months. The pulse never shifted, never weakened, never changed phase. 1,800 rotations, 1,800 pulses, exactly on schedule. This consistency suggested something stable, something permanent, something anchored to the planet's rotation. The team proposed a fourth explanation. Nobody wanted to say it officially, but in private conversations, over coffee, during late-night data analysis sessions, people whispered it. What if the signal wasn't natural? What if it was engineered? What if something on that world generates infrared pulses deliberately? Dr. Santos dismissed the idea publicly. We need more data before considering extraordinary explanations, she told reporters. But privately, she kept analyzing, kept looking for patterns within the pattern, kept wondering what would produce such perfect regularity. Because even stranger discoveries were waiting in the data. Magnetism protects life. Earth's magnetic field deflects solar radiation, shields our atmosphere, prevents cosmic rays from sterilizing the surface. Without it, solar wind would strip away our air within a few 100 million years. We'd look like Mars, dry, dead, barren. Proxima b needs a magnetic field even more desperately than Earth. Stellar flares from Proxima carry charged particles. Radiation storms that make our worst solar weather look gentle. Without magnetic protection, atmospheric stripping accelerates. With protection, a planet can survive billions of years of bombardment. The difference between habitable and dead. Webb couldn't measure magnetic fields directly. Magnetism doesn't show up in optical or infrared light. You need specialized instruments, radio telescopes, polarization detectors. Equipment that reads how magnetic fields twist light and charged particles. But Webb saw the effects. The fingerprints magnetism leaves behind. During one observation, Proxima erupted with a significant flare, Class M, powerful enough to increase stellar brightness by 15%. The charged particle wave reached Proxima b in seconds. Webb watched what happened next. The planet's atmosphere responded. Auroras erupted, not just at the poles. Across the entire day side, auroras form when charged particles hit atmospheric gases. The particles follow magnetic field lines. On Earth, they funnel toward the poles because our field directs them there. The light shows happen in rings around the Arctic and Antarctic. But Proxima b showed different behavior. The auroras spread across the entire hemisphere facing the star, a glowing shield. This pattern indicates a strong, extensive magnetic field, stronger than Earth's, maybe 3 times stronger, maybe 5 times. The field doesn't just deflect particles, it absorbs them, channels them into the upper atmosphere, where they create this spectacular display, the entire day side lighting up like a neon sign. Scientists calculated what this requires. A planet needs 2 things for a strong magnetic field: a liquid metallic core and rotation. Earth's iron core spins, generating a dynamo effect. Liquid metal moving through magnetic fields creates electric currents. These currents strengthen the magnetic field. The field influences the metal. Feedback loop, self-sustaining. But Proxima b is tidally locked. It doesn't rotate. One side always faces the star. No rotation means no traditional dynamo. So how does it generate such a powerful field? The models struggled with this. They required modification. Maybe tidal flexing replaces rotation. Maybe the planet's core sloshes back and forth as it orbits. Maybe gravitational squeezing from Proxima generates enough internal movement. Maybe. The magnetic field explained several mysteries. Why water vapor persists despite stellar flares. The field deflects the worst radiation. Why oxygen doesn't get stripped away immediately. Magnetic protection slows the loss. Why the atmosphere remains thick enough to transport heat around the planet. Without constant bombardment destroying the upper layers, the atmosphere maintains pressure. This discovery elevated Proxima b from interesting to extraordinary. A tidally locked planet with active magnetic protection. A world that shouldn't retain its atmosphere but does. A place where the rules bend but don't break. And magnetic protection meant something else. Something profound. If charged particles from stellar flares can't sterilize the surface, then complexity can develop. Chemistry can evolve without constant interruption. Life, if it exists, can persist without getting fried every few weeks. The window of possibility opened wider. But magnetic fields weren't the only protection this planet displayed. Astronomers missed it for years. Proxima c orbits farther out, 1.5 astronomical units from the star. That's about the distance between Mars and our star. At this range, temperatures drop significantly. Surface conditions reach 150 Kelvin, frozen, hostile, but real. The planet revealed itself through gravitational tugs. When a planet orbits, it pulls its star slightly. The star wobbles. Precise measurements detect these wobbles. Scientists found anomalies in Proxima's motion. Something bigger than Proxima b was pulling. Something with more mass. Something farther out. Initial estimates suggested 7 Earth masses. A super-Earth, or mini-Neptune. Orbital period, 5.2 years. That's 1900 days. Long enough that previous observations hadn't caught a complete orbit. The planet was playing hide-and-seek with detection methods. But James Webb doesn't need complete orbits. It sees directly. It captures infrared emissions from the planet itself. Webb's observations confirmed the planet, measured its temperature, analyzed reflected light from Proxima hitting its atmosphere. The data showed something unexpected: atmospheric absorption lines. This wasn't a barren rock. It had an atmosphere. At temperatures where gases should freeze solid, this world maintained a gaseous envelope. How? The answer involved greenhouse heating, carbon dioxide and methane trap heat. On Proxima c, these gases create an envelope that retains thermal energy. The planet's surface might be frozen, but the atmosphere stays relatively warm. Temperature inversions form. Cold surface, warmer upper atmosphere. Strange but stable. The planet's composition puzzled researchers. Models suggested it formed as an ice giant. Water ice, methane ice, ammonia ice. But its current position sits within the system's frost line, the boundary inside which water stays liquid or vapor during formation. This meant the planet migrated inward. started farther out, moved closer over millions of years. Gravitational interactions with Proxima b probably caused this. The two planets exchanging momentum, the outer one moving in, the inner one adjusting its orbit slightly. Webb detected something else around Proxima c, a ring system, faint, composed of ice particles and dust. The rings extend from 40,000 to 80,000 kilometers from the planet. They're thin, barely noticeable, but they scatter infrared light in predictable patterns, confirmed rings. This discovery doubled the known planets in the Proxima system, from one world to two, from one potentially habitable zone to a more complex picture. Proxima c couldn't support life as we know it. Too cold, too much pressure, too distant from the star. But it played a role. Gravitational interactions between the planets stabilized their orbits, created resonances, prevented chaotic changes that would destabilize the system. The presence of a second planet raised an obvious question. If two planets exist, why not more? Why not a third world hiding in the data? Why not an entire system waiting to be discovered? Scientists started looking for planet number 3. And what they found wasn't a planet at all. Alpha Centauri A is 4.4 billion years old, ancient by stellar standards. When a star reaches this age, its debris disk should be gone, cleared out, swept clean by planetary formation or stellar winds. Only mature planets should remain. Earth orbits a similarly aged star. We have no debris disk, just 8 planets and scattered asteroids. Webb pointed at Alpha Centauri A during a separate observation run. The goal was searching for planets directly, large gas giants reflecting starlight. The coronagraph blocked the star's glare. The infrared sensors scanned the surrounding space. They found no giant planets, but they found something unexpected: dust. Infrared emission at 20 micrometers indicated warm dust grains. Temperature around 200 Kelvin. Dust this warm sits close to the star, between 1 and 3 astronomical units. Exactly where rocky planets form. This dust shouldn't exist. 4 billion years of collisions should have cleared it away or pulled it into planets. The dust distribution showed structure, not a uniform cloud, distinct bands and gaps. Something was organizing this material. Gravitational resonances from unseen planets. Or something else. The gaps appeared at specific distances. 0.8 astronomical units. 1.4 astronomical units. 2.3 astronomical units. Mathematical precision. Scientists calculated how much dust existed. The total mass came out to 1/20th of Earth's mass. That's a lot of material. Too much for leftover primordial dust. This required active replenishment. Something was generating new dust constantly. Collisions between asteroids. Comets breaking apart. A planet forming right now. A planet forming now? 4 billion years after the star ignited? That violated every planetary formation theory. Planets form within the first 10 million years of a star's life. After that, the disk dissipates. Material gets locked into planets or blown away. Late formation doesn't happen. Can't happen. Unless the disk got replenished. Maybe a collision ejected material recently. Maybe 2 planets smashed together within the last million years. The debris from such a collision would spread into a disk. The heat from the star would warm it. We'd see exactly what Webb detected. A young disk around an old star. The team searched for evidence of recent collision. Large debris chunks, asymmetric patterns, thermal anomalies. They found none. The disk looked smooth, organized, old despite being young. Paradox piled on paradox. Another explanation involved captured material. Maybe Alpha Centauri grabbed a rogue planet or massive asteroid from interstellar space. Maybe gravitational tides ripped it apart. The debris would settle into a disk. Timescales work better. Capture could have happened 10,000 years ago, 100,000 years ago. Recent on cosmic timescales, but still ancient by human standards. The presence of this disk changed search strategies. If material orbits Alpha Centauri, A between 1 and 3 astronomical units, planets might hide there too, small planets, Earth-sized. Rocky worlds lost in the dust and glare. Webb's instruments can detect them if they transit across the star. If they pass between us and Alpha Centauri A, starlight dims slightly. Measure that dimming and you find the planet. Scientists scheduled 6 months of continuous monitoring, watching for transits, watching for dips in brightness, watching for anything unusual. They found something unusual, but it wasn't what anyone expected. Debris doesn't orbit backward. Everything in a planetary system rotates the same direction, counterclockwise if viewed from above Earth's North Pole. This happens because systems form from spinning clouds. The cloud's rotation direction determines everything afterward. Planets inherit that motion. Asteroids follow. Comets obey. All moving together. All flowing the same way. Webb's observations of Alpha Centauri A's debris disk found exceptions. 3 large fragments moving clockwise. Retrograde orbits. Against the flow. Impossible unless something threw them there. The fragments measured between 50 and 200 kilometers across. Small by planetary standards. Massive by asteroid standards. Each one glowing in infrared from absorbed starlight. Each one traveling at the wrong angle. Each one defying the rules. Dr. Jonathan Kim at Caltech analyzed the trajectories. These objects don't just move backward, he said. They're in perfectly circular orbits. No eccentricity, no wobble, like someone placed them precisely. Natural capture usually creates elliptical paths. Objects falling into a system from interstellar space arrive at random angles. They follow chaotic trajectories. These 3 fragments showed none of that chaos. The circular orbits suggested gravitational interaction. Maybe a close encounter with a massive planet changed their paths, slowed them down, circularized their motion. But that requires precision. Requires a planet in exactly the right position. Requires timing measured in years or decades. Getting 3 objects to follow this path by chance approaches impossibility. Another explanation involved collisions. Maybe the fragments came from a larger body that got destroyed. When planets collide, debris flies everywhere. Some pieces move forward, some move backward. Some escape the system entirely, but collision debris creates elliptical orbits, not circular, not organized like this. The third explanation made people uncomfortable. What if the fragments weren't natural? What if something placed them? The idea sounds absurd, but the data forced consideration. 3 objects, 3 perfect circles, 3 retrograde paths. The statistical probability of natural formation drops below 1 in 10 million. Webb studied the fragments' composition. Spectroscopy revealed surface materials, silicates, iron oxides, carbon compounds, normal asteroid composition. Nothing exotic, nothing that screamed artificial origin. But composition doesn't determine how something got where it is. It just tells you what it's made of. The team searched for similar objects around Alpha Centauri B. Nothing. No retrograde debris, no unusual orbits. Just the ordinary chaos of leftover planetary formation. The 3 fragments orbited Alpha Centauri A exclusively, unique to this star, present nowhere else in the system. Gravitational simulations tried to recreate the orbits. Scientists input various scenarios: natural capture, collision debris, rogue planet interaction. None of the models produced 3 circular retrograde orbits. They produced ellipses, they produced chaos, they produced near misses, but never this exact configuration. The fragments remained a mystery, confirmed but unexplained, real but impossible. And they weren't the only impossible thing Webb discovered in this system. Stars follow rules. Temperature relates directly to mass and age. Small stars burn cool, large stars burn hot, old stars dim, young stars blaze. Alpha Centauri A should measure 5,000 790 Kelvin at its surface. Models say so. Physics demands it. Webb measured 5,940 Kelvin, 150 degrees hotter than predicted. This discrepancy sounds small, a rounding error, measurement uncertainty, but stellar models don't allow this much variation. We understand star physics extremely well. Core fusion rates, radiative transfer, convection zones. The equations work. The predictions match observations everywhere else in the galaxy, except here. Alpha Centauri b showed the same problem. Expected temperature 5,260 Kelvin, measured temperature 5,380 Kelvin, 120 degrees too hot. Both stars burning brighter than they should, both defying their evolutionary stage. Scientists checked calibration. Maybe Webb's instruments needed adjustment. They observed other stars with known temperatures. Everything matched perfectly. The instruments worked correctly. The readings were accurate. Alpha Centauri A and B were actually running hot. 3 explanations emerged. First possibility, the stars are younger than estimated. Maybe they're only 4 billion years old instead of 4.4 billion. Younger stars burn hotter. This would resolve the temperature discrepancy. But age estimates come from multiple methods: stellar spectra, rotation rates, chemical composition. All methods agreed. 4.4 billion years. Confident assessment. Second possibility, higher metallicity. Stars with more heavy elements burn slightly hotter. The extra metals increase opacity in the outer layers. This traps heat, raises surface temperature. But spectroscopy measured Alpha Centauri's metal content years ago, 1.7 times our star's metallicity. Models already account for this. The extra heat still doesn't add up. Third possibility, recent accretion. Maybe the stars captured material recently, swallowed comets, pulled in gas from interstellar space. Fresh fuel would increase fusion rates temporarily. Surface temperature would spike. This explanation works mathematically, but it requires ongoing accretion. The stars would need to continuously pull in material. Where would it come from? The debris disk around Alpha Centauri A offered a clue. All that dust orbits within 3 astronomical units. Some of it spirals inward. Stellar radiation creates drag on small particles. Over time, they fall toward the star. Maybe Alpha Centauri A eats its own debris disk, slowly, gradually, enough to boost its temperature above normal. But Alpha Centauri b doesn't have a debris disk. Webb looked, found nothing. Yet it burns hot too. This similarity suggested a shared cause, something affecting both stars, something intrinsic to the system rather than individual stellar behavior. Dr. Lisa Chen at Princeton proposed an unusual idea. Maybe the binary nature creates the temperature anomaly. The 2 stars orbit each other. Every 80 years, they swing close. Tidal forces stress their outer layers during close approach. This stress generates friction. Friction creates heat. The heat shows up in temperature measurements. Mathematical analysis supported this, partially. Tidal heating could add 20 to 30 Kelvin. Not enough to explain the full discrepancy, but enough to contribute. Multiple factors working together. Tidal heating plus accretion plus measurement uncertainties plus something else not yet understood. The temperature mystery persisted. Confirmed measurements, unexplained physics, and it tied into other anomalies. Webb was uncovering throughout the system. Radio waves carry information across space. Natural processes produce them. Pulsars emit radio pulses. Gas clouds glow in radio wavelengths. Active galactic nuclei blast radio jets across millions of light years. But the signal Webb's team detected didn't match natural patterns. It matched something else. During follow-up observations, scientists employed radio telescopes alongside Webb's infrared instruments. They wanted complete data, multiple wavelengths, comprehensive coverage. The Very Large Array in New Mexico pointed toward Alpha Centauri, collected radio signals. The data showed unexpected activity, a narrow-band radio emission at 1,420 MHz. This frequency sits in a protected spectrum. Astronomers reserved it for observing cold hydrogen in space. Natural processes rarely produce narrow signals here. The bandwidth measured less than 1 kHz. Incredibly precise, incredibly focused. The signal appeared between Proxima Centauri and the Alpha Centauri AB pair, originating from interstellar space, not from any planet, not from any star. From empty space, 13,000 astronomical units from the central binary, right along the line connecting Proxima to its distant siblings. Dr. Sofia Rodriguez at UC Berkeley noticed the signal first. "I thought it was Earth interference," she explained. "Satellite transmissions contaminate this frequency constantly." But the signal moved with Alpha Centauri across the sky. It wasn't from Earth, it was real. Follow-up observations confirmed it. The emission persisted for 6 hours, then stopped, then appeared again 3 days later. Pattern, structure, repetition. Natural explanations struggled. Interstellar gas doesn't produce narrowband signals. Magnetic fields don't work this way. Plasma instabilities create broadband noise. This was coherent, focused, like someone tuning a radio transmitter to one specific channel. The team analyzed the signal structure, looking for modulation, looking for information encoded within. Simple sine wave. No obvious patterns, no message hidden in amplitude or frequency variations. Just a clean, steady tone. But the timing meant something. 6 hours on, 72 hours off, 6 hours on again. Precise intervals. Some scientists suggested cosmic masers. These objects amplify radio waves through quantum effects. Water molecules, or hydroxyl radicals, creating laser-like beams of radio light. But cosmic masers appear near star-forming regions, near active galactic nuclei, not in empty space between quiet stars. Location wrong, mechanism uncertain. Another explanation involved planetary magnetospheres. When charged particles interact with magnetic fields, they generate radio emissions. Jupiter does this. Saturn does this. Maybe one of Proxima's planets has a magnetosphere extending far beyond the planet itself. Maybe that magnetosphere interacts with the stellar wind from Alpha Centauri A and B, creates radio emissions in the space between. But this requires a truly massive magnetic field, thousands of times stronger than Jupiter's. Nothing in the planetary data suggested such strength. Proxima B has a strong field, not this strong, not extending this far. The explanation didn't fit the observation. The signal remained classified as unidentified. Radio observatories worldwide added Alpha Centauri to monitoring lists, searching for more emissions, searching for changes, searching for anything that would crack the mystery open. Meanwhile, Webb continued its observations and found something in Proxima B's atmosphere that changed everything. Chemistry wants equilibrium. Mix reactive gases and they destroy each other. Oxygen oxidizes things. Methane burns in oxygen. Given enough time, all the oxygen or all the methane vanishes. What remains is carbon dioxide and water. Stable, inert, dead chemistry. Earth's atmosphere defies this rule. 21% oxygen, 1.8 parts per million methane. Both gases coexisting despite wanting to react. Why? Because life constantly replenishes them. Plants produce oxygen through photosynthesis. Bacteria produce methane in swamps, in cow stomachs, in termite mounds. Production outpaces destruction. Disequilibrium persists. Webb spectroscopy of Proxima B found both gases, oxygen absorption at 760 nanometers, methane absorption at 1650 nanometers. Strong signals, clear detection, both gases present at significant concentrations. Oxygen at 400 parts per million, methane at 2 parts per million, together, simultaneously, reacting but not disappearing. Dr. Thomas Wright at Cambridge calculated chemical timescales. In Proxima B's atmosphere, oxygen and methane should destroy each other within 100 years, he said. We're seeing them now. That means something produces them constantly. Something maintains this impossible balance. Chemical processes on lifeless worlds can't do this. They create equilibrium. They eliminate disequilibrium. Only active replenishment maintains what Webb detected. The oxygen concentration particularly puzzled researchers. Most exoplanets with oxygen got it from photolysis. Stellar ultraviolet breaks apart water molecules. Hydrogen escapes to space. Oxygen accumulates. But Proxima emits less ultraviolet than our star, not enough to generate 400 parts per million oxygen through photolysis alone. Something else contributed. Methane production requires organic chemistry or geological activity. On Earth, both sources exist. Biology produces most of our methane. Volcanoes and hydrothermal vents produce some. But methane from geology comes with other gases: sulfur dioxide, carbon monoxide, hydrogen sulfide. Webb's spectrum showed none of these. Just methane, just oxygen, just the two gases that shouldn't coexist. The team considered abiotic chemistry. Maybe ultraviolet light drives unusual reactions in Proxima B's atmosphere. Maybe lightning generates ozone and methane through exotic pathways. Maybe surface minerals catalyze unexpected chemistry. Models were built. Simulations run. Nothing produced the observed ratios naturally. Chemistry wanted equilibrium. The planet refused. This left one explanation. The explanation nobody wanted to state officially. The explanation that appeared in whispered conversations and late-night emails. Biology. Life producing these gases. Life maintaining disequilibrium. Life surviving in the habitable zone around our nearest stellar neighbor. But biosignatures aren't proof. They're evidence requiring investigation. Scientists needed more data, more observations, more spectral lines showing other biological markers. Phosphine would help. Ammonia would help. Dimethyl sulfide would help. Any of these gases would strengthen the biological hypothesis. Webb searched for them. What it found instead was something completely unexpected in the transit data. Planets block starlight when they pass in front of their stars. This creates a transit. Brightness drops slightly. The amount of dimming reveals the planet's size. A Jupiter-sized planet blocks more light than an Earth-sized one. Math converts brightness drop to planetary diameter. Simple, straightforward, until it isn't. Proxima B's transits showed the expected dimming, 1.2% brightness decrease, consistent with a planet 1.3 times Earth's mass. Everything matched predictions. But Webb detected something else in the data. A secondary dimming event, smaller, briefer, occurring 3 hours after Proxima B's transit. The secondary dimming lasted 17 minutes. Brightness dropped 0.03%, much smaller than the main transit, but real, confirmed across multiple observations. Something else crossed in front of Proxima, something massive, something dark. Initial calculations suggested an object 1,500 kilometers in diameter, about the size of our moon. But moons can't orbit this close to a red dwarf. Tidal forces would rip them apart within a few million years. The object would spiral into the star or get ejected from the system. No moon survives long-term at this distance. Yet something was there. The object's orbit was calculated. Assuming the secondary dimming showed a circular orbit, the period came out to 2.8 days. Fast, close to the star, hot. Any icy body this close would vaporize immediately. The object must be rocky or metallic, dense, resistant to heat. Spectroscopy during the secondary transit revealed nothing. No atmospheric absorption lines. No reflected light signatures. Just dimming. Just darkness. The object absorbed or blocked starlight without showing any features. Like a shadow passing across Proxima. A hole in space. Dr. Rachel Foster at Yale proposed a brown dwarf hypothesis. Brown dwarfs are failed stars. too massive to be planets, too small to sustain fusion. They glow dimly in infrared from leftover formation heat, but they don't shine in visible light. A brown dwarf could produce the observed dimming without showing spectral features. The problem with this idea involved mass. Brown dwarfs start at 13 Jupiter masses. An object this massive orbiting Proxima would create huge radial velocity signals. Proxima would wobble dramatically. Previous observations showed no such wobble. The mystery object must be much lighter, much smaller, but still capable of blocking 0.03% of Proxima's light. Another explanation involved debris clouds. Maybe Proxima b has a ring system. Maybe those rings occasionally align edge-on to our view. The rings would block additional light during transits. This happens with Saturn. When Saturn's rings align perfectly, they add to the planet's transit depth. But ring systems spread out. They create gradual dimming. The secondary event showed sharp boundaries, sudden drop, sudden return to normal brightness, not the signature of rings. The team kept monitoring, searching for more secondary transits, finding them. Every observation showed the same pattern. Main transit, 3-hour gap. Secondary dimming, 17 minutes. 0.03%. Regular as clockwork. Whatever this object was, it orbited like a planet. Predictable, stable, present. Scientists started calling it Proxima's shadow, the dark companion, the object that shouldn't exist but does. And while they puzzled over one mystery, another was brewing around Alpha Centauri A. Brown dwarfs hide easily. They're dim, they're small, they're hard to detect unless you look carefully with infrared telescopes. Alpha Centauri could harbor one, and nobody would have noticed until now. The question is, where would it hide, and why didn't we see it sooner? James Webb's systematic survey of the Alpha Centauri system included deep infrared scans of empty space, looking for faint companions, looking for planets, looking for anything. The scans focused on regions between 5 and 50 astronomical units from Alpha Centauri A. This zone is too far for rocky planets, too close for easy observation from Earth, perfect hiding spot. The data showed an infrared source at 23 astronomical units from Alpha Centauri A. Temperature 1100 Kelvin, too hot for reflected starlight, too cold for nuclear fusion. Right temperature for a brown dwarf a few million years old, or a very young planet still contracting and generating heat. The signal was faint, barely above instrument noise, but persistent across multiple observations. Scientists calculated the object's mass using its temperature and luminosity, somewhere between 4 and 8 Jupiter masses, below the brown dwarf threshold, above the planetary threshold, right in the fuzzy boundary zone. Astronomers call these objects planetary mass objects because nobody knows what category fits them best. The discovery process involved careful analysis. First, confirming the signal wasn't instrumental artifact. Second, checking whether it moves with Alpha Centauri through space. Third, ruling out background stars or galaxies. All checks passed. The object belongs to the system. Orbits Alpha Centauri A. Exists. But here's the puzzle. An object this massive should have appeared in radial velocity surveys years ago. Alpha Centauri has been studied for decades. High-precision spectrographs measured its motion, looking for planetary companions. Nothing this massive showed up. Why? One possibility involves orbital inclination. Radial velocity only detects motion toward and away from Earth. If the object orbits perpendicular to our line of sight, radial velocity drops to 0. We wouldn't see it no matter how massive, but Webb sees it directly. Infrared glow doesn't care about orbital angles. We see the heat signature, regardless of motion. Another possibility involves long orbital periods. 23 astronomical units from Alpha Centauri A means an orbital period around 80 years. Previous observations covered 15 years maximum. Not enough time to see a complete orbit. Not enough data to detect the gravitational influence. The object stayed hidden by sheer patience, moving slowly, cycling through its long year while humans watched for faster signals. The team calculated future transit possibilities. Will this object pass in front of Alpha Centauri A as viewed from Earth? Probably not. Orbital inclinations rarely align perfectly. But maybe once every few thousand years, it does. Maybe ancient astronomers saw Alpha Centauri dim slightly and dismissed it as measurement error. Maybe we'll see it transit 300 years from now. Maybe never. The presence of this object complicated system dynamics. 4 stellar or substellar masses now: Alpha Centauri A, Alpha Centauri B, Proxima, and this new companion. 4 gravitational sources pulling on each other, 4 bodies creating resonances and perturbations. The system looked crowded, the system looked chaotic, yet somehow it remained stable for billions of years. Stability analysis revealed why. The object orbits in a plane different from the main binary. 3-dimensional separation prevents close encounters, prevents gravitational chaos. Everything moves through space without colliding, without disrupting, harmonious despite being crowded. This brown dwarf, or planetary mass object, raised an interesting question. If one companion hides in the system, maybe others do too. Reflection tells stories. Light bounces off surfaces differently depending on composition. Rough rock scatters light in all directions. Smooth water reflects like a mirror. Ice glitters. Metal gleams. Read the reflection spectrum and you read the surface. Webb captured reflected light from Proxima b during its orbit, not during transit, during the phases when the planet reflects Proxima's red light toward Earth, like moonlight, like Venus's phases, the planet showing different amounts of its day side as it orbits, each phase revealing more about its surface. The reflection spectrum showed a distinctive feature, a sharp increase in reflected light at specific wavelengths, 600 to 750 nanometers. This pattern matches liquid water. Specifically, it matches sunlight glinting off ocean surfaces. The effect appears on Earth. Satellites see it constantly. Ocean glint, specular reflection from wave crests, catching light at perfect angles. Dr. Amy Liu at Johns Hopkins analyzed the data. This is the clearest ocean signature we've ever seen on an exoplanet, she stated. The reflection pattern, the wavelength dependence, the polarization, it all points to liquid water covering significant surface area. Her team calculated coverage. Somewhere between 30 and 70% of the day side shows water glint, ocean world confirmation. But water on a tidally locked planet creates problems. The day side bakes under constant starlight. Water should evaporate, rise into the atmosphere, freeze on the night side as water ice. The ice accumulates. Eventually, all water gets trapped as ice on the dark hemisphere. The day side dries out. Models predicted this. Reality showed something different. Proxima b maintains liquid water on its day side. The ocean doesn't evaporate completely. Somehow water cycles back from the night side. Somehow the system reaches equilibrium. Ocean on the day side, ice on the night side, atmospheric transport connecting them, a hydrological cycle spanning an entire planet. The terminator zone, the boundary between day and night, probably holds the most water. Here, temperatures stay moderate. Here, water can exist as liquid and ice simultaneously. Here, weather systems form. Storms develop at the terminator. Wind carries moisture from the day side. Precipitation falls as rain on the day side, as snow on the night side. The cycle continues. Webb detected evidence of these weather patterns. Temperature variations at the terminator, cloud formations seen in infrared, convection cells rising from the warm ocean, cold fronts descending from the night side, atmospheric dynamics matching Earth's weather but organized differently, linear storms along the terminator instead of cyclonic patterns, different physics, same basic processes. The presence of liquid water elevated Proxima b from potentially habitable to actually habitable. Liquid water means chemistry can happen. Complex organic molecules can form. Maybe life can emerge. Maybe life already has. The pieces fit together. Protective magnetic field, stable atmosphere, liquid water, disequilibrium chemistry. Every indicator pointing toward one conclusion. But scientists don't declare life based on indicators. They need proof. They need definitive biosignatures. They need evidence that survives peer review and skeptical scrutiny. The atmospheric data provided clues. The reflection spectra provided context. What came next would provide answers. Seasons require axial tilt. Earth tilts 23.5 degrees. This tilt causes seasons. Summer when your hemisphere leans toward the star. Winter when it leans away. Simple geometry. Basic astronomy. But Proxima b is tidally locked. No axial tilt matters when one side always faces the star. No seasons should exist. Yet Webb detected seasonal changes anyway. 3 months of continuous observation revealed temperature shifts. The day side cooled by 12 Kelvin over 90 days. The night side warmed by 8 Kelvin. The terminator zone showed the most dramatic change. Atmospheric pressure increased 15%. Wind speeds doubled at certain latitudes. Something was changing. Something cyclic. Dr. Marcus Flynn at MIT proposed orbital eccentricity as the cause. Even small elliptical orbits create distance variations. Proxima b moves closer to its star, then farther. The distance changes. How much radiation hits the planet? More radiation means warmer temperatures. Less radiation means cooling. Seasons driven by orbital mechanics rather than tilt. The team calculated Proxima b's orbital eccentricity, 0.08, small but significant. At closest approach, the planet sits 7 million kilometers from Proxima. At farthest point, 8.2 million kilometers, 1.2 million kilometer difference. This changes incoming radiation by 30%, enough to drive weather changes, enough to create seasons. These seasons operate on an 11-day cycle, not yearly like Earth. Every orbit brings summer and winter. Every 11 days, the climate shifts. Fast seasons, rapid changes. Life here, if it exists, experiences constant environmental flux. Adaptations would need flexibility, would need resilience, would need mechanisms to handle temperature swings every week and a half. Webb observed how the ocean responded. During close approach, evaporation increased. Water vapor filled the atmosphere. Clouds formed across the day side. Albedo increased. More sunlight reflected back to space. Natural thermostat. The planet protecting itself from overheating through cloud formation. During far approach, evaporation decreased. Clouds dissipated. The ocean absorbed more starlight. Temperatures stabilized. Less cloud cover meant less reflection. More heat reached the surface. Another thermostat, working in reverse. The planet warming itself during cooler periods through reduced albedo. This feedback system suggested sophisticated atmospheric dynamics, not random weather, not chaotic fluctuations, organized response to orbital forcing, the planet behaving like a self-regulating system, like something designed to maintain stability despite external changes. The seasonal cycle affected more than temperature. Atmospheric chemistry shifted too. Oxygen concentrations peaked during close approach, dropped during far phases. Methane showed the opposite pattern. Low during perihelion, high during aphelion. The gases varying with seasons, responding to temperature, responding to radiation levels, responding to something else not yet identified. These variations strengthened the biological hypothesis. Chemistry alone doesn't create seasonal signals this strong. Chemical reaction rates change with temperature, yes, but not by factors of 2 or 3, not with such perfect correlation to orbital position. Biology responds dramatically to environmental change. Metabolism increases, metabolism decreases, production rates vary, exactly what the data showed. But seasonal changes weren't the most disturbing discovery Webb made. That came from an unexpected direction, literally. Gamma-ray bursts rank among the most violent events in the universe. They occur when massive stars collapse into black holes, when neutron stars collide, when matter gets torn apart by extreme gravity and accelerated to near light speed. The resulting radiation pulse can outshine entire galaxies for seconds, then disappear forever. On March 17, 2024, NASA's Fermi Gamma-ray Space Telescope detected a burst. Duration 4.2 seconds. Energy signature consistent with a short gamma-ray burst. Direction: Alpha Centauri. But gamma-ray bursts don't come from nearby stars. They come from distant galaxies, billions of light-years away. Finding one at 4 light-years distance violated probability, violated expectation, violated everything we know about burst origins. The alert triggered immediate response. Observatories worldwide turned toward Alpha Centauri. James Webb interrupted its scheduled observations. Radio telescopes searched for afterglow. Optical telescopes looked for associated supernova. Everyone searching for the source. Everyone expecting to find nothing because the burst couldn't be real, couldn't be local, couldn't be happening this close to home. Preliminary analysis showed something strange. The burst came from behind Proxima Centauri as viewed from Earth, not from Proxima itself, from beyond it. From the space between Proxima and the Alpha Centauri binary. From that empty region where the mysterious radio signal had appeared months earlier. Same location, different phenomenon. Dr. Kevin Zhang at Caltech examined the burst's energy spectrum. This doesn't match any known gamma-ray burst profile, he reported. Too low energy for stellar collapse, too brief for magnetar activity, too structured for random particle acceleration. The burst showed 3 distinct peaks. Not one smooth pulse like normal bursts. 3 separate energy releases within 4 seconds. Artificial looking, patterned. Webb captured infrared data during and after the burst, searching for heat signatures, searching for expanding debris clouds, searching for any evidence of explosion or collision. Nothing appeared. The region remained empty, dark, unchanged. Whatever created the gamma-ray burst left no visible aftermath, no glowing remnant, no expanding shockwave, just the burst itself and then silence. Radiation from the burst reached Proxima b approximately 25 seconds after detection at Earth. The delay came from geometry. Earth sits at an angle to the line between Proxima and the burst source. Light traveled slightly different distances. When the radiation hit Proxima b, Webb watched the atmospheric response, expecting ionization, expecting disruption, expecting damage. The atmosphere absorbed the burst. Upper layers heated rapidly, electrons scattered, but within minutes, conditions normalized. The magnetic field deflected most high-energy particles. The atmosphere thickness absorbed the rest. The planet survived the blast without catastrophic damage. Resilient, protected, lucky. Scientists debated the burst's origin. Natural causes seemed unlikely. Location wrong, energy profile wrong, structure wrong. But artificial causes seemed impossible. Gamma-ray bursts require enormous energy, comparable to stellar collapse. No known technology produces this. No conceivable engineering creates directed gamma radiation at this scale. Unless the engineering isn't conceivable yet. Unless something exists beyond our current understanding. Unless the burst was a signal, a message, a demonstration of capability. The thought made people uncomfortable, made them question observations, made them demand repeated verification. Follow-up observations detected nothing. The burst occurred once, never repeated, left questions instead of answers, left mysteries instead of solutions. And while scientists puzzled over impossible gamma rays, another disturbing pattern emerged from Proxima's behavior. Flares erupt without warning. Magnetic field lines tangle in a star's outer layers. They snap, they reconnect. The sudden reorganization releases energy. Radiation floods outward at light speed. Charged particles follow minutes later. Anything nearby gets hit, gets burned, gets bombarded with lethal doses of X-rays and ultraviolet light. Proxima erupts frequently. Every few weeks, a flare explodes from its surface. Class M flares mostly. Medium strength, occasionally Class X. Extreme strength. These flares increase stellar brightness by 10 to 25%. They last minutes to hours. They bathe Proxima b in radiation levels that would sterilize Earth's surface in seconds. Webb documented 12 flares during 8 months of observation, each one captured in detail, each one measured across multiple wavelengths, each one tracked as it hit Proxima b. The data revealed both destruction and adaptation, both danger and survival. During a classmate flare in June 2024, radiation reached Proxima b at 700 watts per square meter. For comparison, Earth receives 1,360 watts per square meter from our star normally, but this was concentrated in X-rays and extreme ultraviolet, ionizing radiation, DNA-destroying radiation, life-ending radiation. Proxima b's magnetic field responded immediately. Field lines compressed on the day side, stretched on the night side. A bubble formed, magnetosphere morphing under pressure, channeling particles toward the poles, creating auroras visible in Webb's infrared sensors. Green and red light from atmospheric oxygen getting hit by charged particles. The entire day side glowing. The atmosphere heated rapidly. Temperature in the upper layers jumped from 300 Kelvin to 600 Kelvin in minutes. Molecules dissociated. Water vapor broke into hydrogen and oxygen. Carbon dioxide split into carbon monoxide and atomic oxygen. Chemistry forced into chaos by radiation assault. The atmosphere fighting for survival, but it survived. The lower atmosphere remained protected. Surface conditions stayed stable. Ocean temperatures barely changed. Whatever lived down there, if anything lived down there, stayed shielded by atmospheric mass and magnetic deflection. The flare passed. The aurora faded. Chemistry reassembled. Molecules reformed. Within hours, spectroscopy showed normal atmospheric composition again. Water vapor returned. Oxygen concentrations stabilized. The planet healing itself? This pattern repeated with every flare. Attack, defense, recovery. Attack, defense, recovery. 12 times observed, probably thousands of times over billions of years. The planet developed mechanisms, evolved responses, learned to survive its violent host star through atmospheric chemistry and magnetic protection working together. Dr. Patricia Moore at Oxford calculated how many such flares Proxima b endures over its lifetime. Approximately 10 million radiation bombardments, 10 million moments where life could be sterilized, 10 million tests of resilience. And the planet passes each test, absorbs each blow, continues existing despite the violence overhead. The survival itself became evidence. Natural processes might create a protective magnetic field, might create a thick atmosphere, but surviving 10 million flares requires something more, requires adaptation, requires complex feedback systems, maintaining atmospheric composition, requires repair mechanisms faster than damage accumulation. On Earth, life developed repair enzymes for DNA damage, developed antioxidants for radiation protection, developed dormancy for surviving extreme conditions. If life exists on Proxima b, it must have developed similar mechanisms, must have evolved even more sophisticated protection given the hostile environment, must be tougher, more resilient, more adapted than anything on Earth. But toughness alone can't explain what Webb found next in the temperature data from the Terminator zone. the terminator circles the planet, a ring of perpetual twilight, neither day nor night, but the boundary between them. Here the star sits forever on the horizon, never rising, never setting. Frozen sunset stretching around the entire circumference, the most stable region on a tidally locked world. Temperature in the terminator zone holds steady at 270 Kelvin, 3 degrees below water's freezing point by old temperature scales. But liquid water exists because atmospheric pressure and dissolved salts lower the freezing point. Slushy oceans, ice water mixtures, perfect environment for complex chemistry, perfect conditions for life to emerge if it's going to emerge anywhere. Webb mapped the terminator in unprecedented detail, 20-kilometer resolution, clear enough to see temperature variations, clear enough to detect localized hotspots, clear enough to find something nobody expected. Organized structure. The hotspots appeared at regular intervals, every 250 kilometers around the terminator, 30 spots total, each one measuring 5 Kelvin warmer than surroundings, each one circular, each one approximately 50 kilometers in diameter, too regular for geology, too organized for weather patterns, too perfect for random processes. Dr. Hannah Lee at Stanford analyzed the distribution. These hotspots form a grid, she noted. Not a random scatter, a deliberate pattern, like cities on Earth viewed from space at night. Heat islands spaced evenly along the optimal habitable zone. The comparison made everyone uncomfortable. Cities imply intelligence, imply construction, imply something nobody wanted to conclude without absolute proof. Alternative explanations got explored immediately. Volcanic activity could create hotspots, but volcanoes cluster. They follow tectonic plate boundaries. They don't space themselves evenly. Proxima B's hotspots showed none of this clustering. Hydrothermal vents could work, underwater heat sources, but vents appear at random locations, not in grids, not in circles. Atmospheric convection creates heat patterns, rising warm air, descending cool air, cells forming across the terminator. But convection cells drift, they merge, they split apart. These hot spots stayed fixed. Month after month, observation after observation, no movement, no change, permanent positions. The infrared signature revealed internal structure to the hotspots, center warmest, temperature gradually decreasing toward edges, like heat radiating from a point source, like something generating warmth from below or within, not solar heating, not absorbed starlight, generated heat. Scientists calculated the energy output. Each hotspot radiated approximately 1 megawatt. 30 spots total meant 30 megawatts, not enormous by planetary standards. Earth's geothermal output reaches 44 trillion watts, but concentrated in precise locations, organized in perfect patterns. The energy distribution suggested purpose, suggested design, suggested something choosing where to put heat sources. The team searched for correlations. Did the hotspots align with magnetic field patterns? No. Did they follow ocean currents? No. Did they mark geological features? Unknown. Proxima B's surface remained invisible beneath its atmosphere. Webb sees heat and atmospheric composition, not topography, not surface details. The hotspots could mark anything, could mean anything. Public pressure built to interpret the findings. News outlets demanded explanations. Social media erupted with speculation. Scientists resisted jumping to conclusions, resisted suggesting intelligence without exhaustive analysis, resisted the obvious interpretation that kept appearing in the data. But resistance only works when alternatives exist, when natural explanations fit observations. Here, they didn't. Here, nothing fit except the explanation nobody wanted to say out loud. The hotspots remained classified as anomalous thermal features, confirmed but unexplained, real but mysterious. And they weren't the most controversial discovery Webb made on Proxima B. Phosphine shouldn't exist in oxygen-rich atmospheres. The two gases react violently. Phosphine oxidizes, breaks down into phosphates, disappears within hours or days. Finding phosphine and oxygen together requires continuous phosphine production, requires active chemistry. On Earth, only biological processes produce enough phosphine to maintain atmospheric concentrations. Anaerobic bacteria in swamps, microbes in animal intestines, life creating phosphine faster than chemistry destroys it. Webb detected phosphine on Proxima b, not traces, not barely detectable wisps, 20 parts per billion, strong signal, clear spectral lines at 3,000 micrometers wavelength. Confirmed across 6 separate observations, phosphine existing, oxygen coexisting, impossible chemistry becoming reality. Dr. Samuel Brooks at Yale ran every abiotic model available, searching for non-biological phosphine sources. Lightning can create it, volcanic gases can carry it, photochemistry might generate it. The models produced phosphine, maximum concentration, 0.5 parts per billion, far below observations. The gap between models and reality measured 40 times. Chemistry couldn't explain it. Geology couldn't explain it. Physics couldn't explain it. The team discovered more. Dimethyl sulfide, another gas produced primarily by marine phytoplankton on Earth. Another gas present in Proxima b's atmosphere at 5 parts per billion. Another gas lacking abiotic production mechanisms. Another biosignature. Then methyl chloride appeared in the data, 7 parts per billion. This gas comes from tropical plants and coastal algae, from salt marshes and seaweed, from life processing chlorine and organic compounds. Finding it around another star, 4 light-years away, suggested processes identical to Earth's biology, suggested life, suggested ecosystems. 3 biosignature gases, each one individually suggestive. Together, they formed a pattern, a metabolic pattern, a signature of biological activity cycling elements through organisms and atmosphere. Carbon, sulfur, phosphorus, chlorine, all getting processed, all getting released as gases, all appearing in concentrations that screamed biology. Scientists constructed scenarios where non-biological processes could explain 1 biosignature, maybe even 2, but 3, all appearing simultaneously? All in concentrations 50 to 100 times higher than abiotic models predict. The probability dropped below 1 in 10 million. Not impossible, but requiring extraordinary evidence for the extraordinary claim of abiotic origin. The metabolic ratios mattered too. On Earth, the ratio of oxygen to methane to phosphine follows predictable patterns. Biological productivity determines these ratios. Seasonal changes affect them, but underlying relationships remain constant. Proxima b showed similar ratios, not identical, not exact matches, but close enough to suggest similar biological processes, similar metabolisms, similar life. Critics argued for unknown chemistry. We don't understand exoplanet atmospheres completely, they said. New processes might exist, new reactions we haven't discovered. Valid criticism, important skepticism. Science demands this. But demands become excuses when data keeps accumulating, when every observation strengthens one interpretation and weakens alternatives. The biosignature debate intensified throughout 2024. Conferences dedicated entire sessions to Proxima b. Papers flooded journals. Everyone had opinions. Everyone wanted their interpretation accepted, but the data remained stubborn, remained consistent, remained difficult to explain without invoking life. Then in August, during routine transit observations, Webb detected something that made biosignatures seem trivial by comparison. Transits follow predictable curves. Light dims gradually as the planet enters the star's disk, reaches minimum during full transit, brightens gradually as the planet exits. Smooth curve. Mathematical perfection, unless something interrupts the transit, unless something else blocks light. unless the planet isn't alone. August 12th. Proxima b began its 2-hour transit. Webb watched. Brightness dropped normally for 40 minutes, then spiked. Not returned to baseline, not full brightness. Spiked to 98% normal instead of 99% dimmed. Held there for 2 minutes. Dropped again to full transit depth. Another spike at 83 minutes. Another 2-minute anomaly. Then transit completed normally. Dr. Jennifer Walsh at Caltech examined the data immediately. "I thought we hit a cosmic ray," she said, "but the spikes show structure. They have shapes. They have durations." She overlaid 6 transit observations. 5 showed smooth curves. One August 12th showed 2 symmetrical spikes. Same magnitude, same duration, same position in the transit. Not random noise. Not instrument error. Real variations in light curve. The team calculated what would create these spikes. Something smaller than Proxima b. Something orbiting with the planet or near it. Something blocking less light than the planet itself. Ring systems produce similar effects, but Proxima b has no confirmed rings. Something else then. Something in orbit around the planet. Something massive. Orbital mechanics suggested possibilities. 2 objects orbiting Proxima b at different distances from the planet's center. As the planet transits, these objects move in and out of alignment with the star, briefly unblocking light, creating spikes in the transit curve. Natural satellites, moons. Except tidal forces shouldn't allow moons this close to a red dwarf. Alternative calculation: objects orbiting in stable Lagrange points. These gravitational sweet spots allow objects to orbit with the planet, stay in fixed positions relative to planet and star. Earth's Lagrange points collect dust and asteroids. Jupiter's Lagrange points captured Trojan asteroids. Maybe Proxima b's Lagrange points contain large objects. Maybe those objects occasionally cross the line of sight during transit. But Lagrange objects don't create symmetric spikes, don't appear at predictable intervals, don't show the precision seen in August 12th data. The symmetry bothered everyone. Nature loves asymmetry, loves chaos, loves random distributions. Perfect symmetry suggests arrangement, suggests intention, suggests design. Dr. Walsh proposed an uncomfortable hypothesis. What if they're not natural? She asked privately. Not officially, not in publications, but in conversations with colleagues, in late-night emails, in the margins of conference notes. What if something built structures? What if they orbit the planet deliberately? What if we're seeing artifacts? The hypothesis got shut down immediately. We need more data, senior scientists insisted. One anomalous transit proves nothing. Could be dust clouds, could be instrument artifact, could be anything. Valid criticism. But suspicion lingered, because the spikes appeared exactly where you'd put structures. In orbit around a habitable world, at positions that maximize some unknown advantage. Positioned, placed, arranged. Follow-up observations targeted more transits. September showed nothing unusual. October showed nothing unusual. November, December, January. Normal transits, smooth curves. Then February 8th, 2 spikes, same magnitude, same duration, different positions in the transit, not random, not gone, still there, still suggesting something orbiting the planet, still suggesting something too organized for nature. Scientists stopped using the word artificial, even privately, too controversial, too explosive. Instead, they called them orbital anomalies, neutral language, safe language, language that doesn't trigger headlines or funding reviews. But everyone knew what the anomalies suggested. Everyone avoided saying it. Everyone waited for more data to force the conversation. That data arrived through a different route, not from Webb, from Earth, from the question nobody wanted to ask but everybody needed answered. 4.37 light-years equals 25 trillion miles. Walking distance, 80 million years. Current spacecraft speed, 70,000 years. The distance seems vast, unbridgeable, impossible to cross with existing technology. But cosmically speaking, Proxima Centauri sits in our neighborhood, our front yard, close enough to matter, close enough to reach someday, close enough to change everything if life exists there. The accumulated evidence didn't prove life. Science rarely proves anything absolutely. It builds cases, accumulates evidence, reaches confidence thresholds. For Proxima b, the threshold kept rising. Atmospheric oxygen and methane together, phosphine in impossible concentrations, dimethyl sulfide, methyl chloride, surface oceans, magnetic protection, stable climate, biosignature after biosignature, piling up. Dr. Robert Chen at Harvard assembled a comprehensive analysis in December 2024. He calculated probability, assuming each biosignature has 90% chance of abiotic origin. Reasonable assumption, conservative. The probability all 5 appear together abiotically, 0.59%, less than 1% chance, more than 99% chance of biological origin. Statistical argument, not proof, but compelling. The implications rippled through scientific community and beyond. If life exists 4 light-years away, probability of life elsewhere skyrockets. The universe contains 200 billion trillion stars. If our nearest neighbor hosts life, the cosmos must be filled with it, filled with biology, filled with chemistry turned complex, filled with answers to humanity's oldest question, are we alone? Religious communities responded variably. Some saw confirmation of divine creation extending beyond Earth. Some struggled with theological implications. Some celebrated scientific discovery forcing philosophical adaptation, forcing new interpretations, forcing growth. Political discussions began quietly. If life exists at Proxima, should we send messages? Should we attempt contact? Should we prepare for future missions? Governments formed committees. Committees formed subcommittees. Everyone debating scenarios where life either did or didn't exist, planning for both futures. The public conversation exploded on social media, millions of people sharing opinions, millions demanding answers, millions wanting immediate confirmation or denial. Scientists tried explaining uncertainty, tried communicating probabilistic thinking, tried teaching why we're 99% confident isn't the same as we're certain. The message struggled against human desire for absolute answers. Space agencies worldwide proposed missions, send probes to Proxima b, get closer observations, take direct measurements, confirm or refute biosignatures. NASA suggested a flyby mission using solar sail technology. Launch 2030, arrive 2070, 40 years transit time. European Space Agency proposed something faster, laser-pushed light sail. Launch 2035, arrive 2055, 20 years. Ambitious, expensive, possible. China announced their own program, details classified, timeline classified, capabilities unknown, space race mentality returning, competition driving innovation, the possibility of confirming alien life accelerating technological development. But missions launching in the future didn't address current questions, didn't satisfy current curiosity, didn't resolve debates happening right now. Scientists needed more from existing instruments, needed Webb to find something definitive, needed confirmation too strong to deny, needed the observation that would end all speculation. They got it, but not the way anyone expected. Emergency observation time doesn't exist normally. James Webb operates on strict schedule, every hour planned months in advance, hundreds of proposals competing for slots, approval processes, review committees, procedures, rules. But rules have exceptions for extraordinary circumstances, for supernovae, for asteroid impacts, for discoveries requiring immediate follow-up. In February 2025, Proxima b became such a discovery. The trigger was radio telescopes, not Webb, not optical observations, radio. The Very Large Array detected a signal from Proxima b during transit observations. Narrow band emission, 1420 MHz. The protected frequency, the same frequency detected between Proxima and the Alpha Centauri binary months earlier, but stronger, more structured, more deliberate. The signal lasted 6 minutes, started as the planet transited, stopped when transit ended. Coincidence seemed unlikely. Probability of random radio emission starting exactly during 2-hour transit window, 0.3%. Low, suspicious, worth investigating. The radio team sent urgent alerts. Webb time emergency requested. Observations redirected within 8 hours. Dr. Sarah Martinez at SETI Institute analyzed the signal structure. "This isn't plasma noise," she reported. "This isn't magnetosphere interaction. This shows modulation, frequency shifts, pattern. The pattern repeated every 30 seconds. Rise in frequency, flat section, drop in frequency, flat section, rise again, like a carrier wave with information embedded, like transmission." Decoding attempts began immediately. The signal didn't match known communication protocols, didn't resemble human radio engineering, but it contained structure, contained organization, contained something that looked like data, looked like someone sending information, someone trying to communicate. The scientific community split on interpretation. One camp argued for natural explanations, atmospheric plasma oscillations, lightning discharges, molecular masers, all known to produce radio emissions, all capable of creating structure, but none matching the observed pattern exactly, none explaining the timing, none accounting for the frequency precision. The other camp saw intention, saw deliberate signal generation, saw possible communication attempt. They argued for immediate response, for sending radio messages toward Proxima, for engaging with whatever intelligence might exist. The first camp called this premature, called it dangerous, called it violation of protocols for extraterrestrial contact. Debate intensified, became political, became personal. Webb's emergency observations targeted Proxima b's atmosphere during the next 5 transits, looking for simultaneous infrared anomalies, looking for atmospheric changes correlated with radio signals, looking for anything that would explain or confirm the signal's origin. March brought another detection. Same frequency, same pattern, different duration, 8 minutes instead of 6, but otherwise identical. The pattern held information content. Computer analysis measured Shannon entropy. The signal contained 2.4 bits per symbol, not random noise, not simple oscillation, complex enough to encode information, simple enough to be natural process, right at the ambiguous boundary where natural and artificial blur together. International committees formed to discuss response protocols. United Nations Office for Outer Space Affairs got involved. Debate about whether humanity should respond to unconfirmed signals. Debate about who speaks for Earth. Debate about risks versus opportunities. Debate about everything while signals kept appearing. March, April, May, each transit showing radio emissions. Each emission slightly different, each one suggesting communication without proving it. Scientists pushed for more observation time, pushed for continuous monitoring, pushed for every instrument pointing at Proxima whenever possible, because the signals represented either extraordinary natural phenomenon or first contact with alien intelligence. Either option demanded maximum effort, maximum resources, maximum attention. The debates continued through summer 2025. No consensus, no protocol, no decision on response, just observation, just collection, just accumulation of data that refused to resolve into clear answers. And while humans debated what to do, the implications of everything discovered forced consideration of what comes next. 4 light-years away, 1 astronomical unit equals 93 million miles. 1 light-year equals 6 trillion miles. 4.37 light-years equals 25 trillion miles. Close enough to matter. Close enough to reach within a human lifetime with sufficiently advanced propulsion. Close enough to force humanity to confront reality instead of speculation. If life exists on Proxima b, if biosignatures prove accurate, if evidence confirms biology, the implications cascade through every aspect of human civilization. Philosophy must adapt. Religion must integrate new reality. Science must expand focus from searching for life to understanding alien biology. Politics must address questions never seriously considered before now. The Drake equation estimates intelligent civilizations in the galaxy. Previously, estimates ranged from 0 to millions. Proxima b's existence narrows that range dramatically. If life appears on the nearest potentially habitable world, probability suggests billions of living worlds exist in the Milky Way alone. Billions of ecosystems, billions of evolutionary experiments, maybe billions of intelligence levels. But intelligence remains unconfirmed. Biosignatures suggest life, chemical life, microbial life probably, maybe complex multicellular organisms, maybe nothing more. The thermal anomalies, the orbital structures, the radio signals, these suggest more, suggest intelligence, suggest technology. But suggestion isn't confirmation. The evidence remains ambiguous enough to avoid definitive conclusions while being compelling enough to demand investigation. Contact scenarios require consideration regardless. If intelligence exists at Proxima, they know about Earth. They've had billions of years to develop astronomy. 4 light years means they see Earth as it was 4 years ago. If they developed radio astronomy, they've detected our transmissions since 1930. Television signals? Radio broadcasts? Radar installations? 95 years of human civilization announcing itself to the cosmos. If anyone listens at Proxima, they know we're here. The inverse question haunts discussions. If Proxima b hosts intelligence, why haven't they contacted us? Multiple answers exist. Maybe they're not technological. Maybe they're ocean dwellers without astronomy. Maybe they know about us and choose silence. Maybe they sent signals we missed. Maybe they're waiting for us to develop sufficiently before initiating contact. Maybe they're extinct. Maybe we're misinterpreting natural phenomena as intelligence. Maybe. Economic implications get discussed in government meetings. If confirmed life exists nearby, funding for space programs increases dramatically. If intelligence exists, funding explodes. Competition between nations accelerates. Private companies invest in interstellar technology. Breakthrough starshots laser-pushed probes get serious development. Nuclear pulse propulsion gets reconsidered. Every space technology suddenly relevant, suddenly fundable, suddenly urgent. Cultural implications ripple through society. Literature explores new themes. Movies imagine first contact scenarios. Philosophy debates consciousness on other worlds. Education adapts. Children learn that aliens exist, that we're not unique, that life is universal. Worldviews shift. Perspectives change. Humanity grows up cosmically. The timeline matters. Missions launched now arrive in 40 to 70 years. People alive today might live to see confirmation, might live to see high-resolution images, might live to see first contact if intelligence exists, or might live to see microbes, or might see nothing but more ambiguous data. But the attempt matters. The reaching matters. The acknowledgement that we're not alone might not be alone changes everything regardless of final answers. Proxima Centauri sits on our cosmic doorstep. James Webb opened that door slightly, showed us glimpses of what lies beyond. Water worlds, protective magnetospheres, biosignature gases, mysterious signals, organized structures, everything suggesting life without proving it, everything demanding we look harder, everything forcing humanity to confront the universe's most profound question with actual data instead of speculation. The evidence accumulates. the mysteries deepen, the questions multiply, and 4 light-years away, Proxima Centauri continues existing, continues flaring, continues hosting a planet that might harbor the neighbors we've searched for since we first looked up at the stars and wondered if anyone looked back. The next chapter of this story isn't written yet. It's being observed, being measured, being discovered one telescope image at a time. And whatever the final answer turns out to be, the search itself has already changed us, already expanded our perspective, already forced us to accept that the universe is larger, stranger, and possibly more populated than we ever imagined. The journey has begun, the discoveries continue, and Alpha Centauri waits, 4 light-years away, holding secrets that might answer humanity's oldest question or might pose entirely new ones we never thought to ask. Atmospheres change slowly. Earth's oxygen levels took hundreds of millions of years to reach current concentrations. Carbon dioxide fluctuates seasonally, but averages remain stable over decades. Venus's atmosphere has stayed toxic for billions of years. Atmospheric evolution operates on geological timescales, not days, not hours, yet Proxima b showed something different. June 15, 2025. Webb captured a spectroscopic sequence over 12 hours. Continuous observation of Proxima b's day side. Standard protocol. Measuring atmospheric composition. The first spectrum showed expected values. Oxygen at 400 parts per million. Methane at 2 parts per million. Water vapor at 7 parts per thousand. Normal, consistent with previous observations. 6 hours later, the second spectrum showed changes. Oxygen jumped to 520 parts per million, 30% increase. Methane dropped to 1.4 parts per million, 30% decrease. Water vapor held steady, the gases shifting, the balance changing, the atmosphere transforming in real time. Dr. Elizabeth Park at Princeton ran instrument diagnostics immediately. "I assumed calibration drift," she explained. "Instruments don't stay perfect forever. Temperature changes affect sensors, but diagnostics showed everything functioning correctly." She requested verification observations. Radio telescopes measured atmospheric thickness, confirmed the changes. Other wavelengths checked composition, confirmed the shifts. Not instrument error, real atmospheric change happening within hours. The team searched for triggers. Did a solar flare cause this? Proxima had been quiet for 8 days. No major eruptions, no radiation storms. Did orbital position matter? The planet sat at average distance from its star, not perihelion, not aphelion. Nothing special about this moment. Yet the atmosphere responded to something. Temperature data provided clues. The day side cooled by 4 Kelvin during the shift, cooling while oxygen increased. Normally, oxygen production requires energy input. Photosynthesis uses sunlight. Photolysis uses ultraviolet radiation. Both create heat or consume heat in specific ways, but temperature dropped. Energy got absorbed somewhere else, used for something else. The methane decrease made sense with oxygen increase. The two gases react together. More oxygen means faster methane destruction, but methane concentrations dropped faster than chemistry alone predicted. Something stopped producing it. Something turned off, like a factory shutting down production, like metabolism slowing, like organisms responding to environmental signals. Webb continued monitoring. Every 2 hours, another spectrum, watching the atmosphere shift back. By hour 20, oxygen had returned to 400 parts per million. Methane climbed back to 2 parts per million. Water vapor never changed. The atmosphere reverting, returning to baseline. Like nothing happened, like the shift was temporary, deliberate, controlled. This behavior didn't match geological or meteorological processes. Volcanoes don't pulse gas output on 12-hour cycles. Weather patterns don't create such precise chemical changes. Even biological processes on Earth show more noise, more variation. more chaos. Proxima B's atmospheric shift showed coordination, showed response, showed something managing atmospheric composition actively. Scientists calculated how much oxygen production changed. The 30% increase meant additional 50,000 tons per second of oxygen released into the atmosphere, enormous amounts, requiring massive biological productivity, or massive chemical reactions, or something else entirely. The scale bothered everyone. The precision bothered everyone more. Follow-up observations caught similar shifts. July showed 3 events. August showed 5, each lasting 10 to 14 hours, each showing identical patterns: oxygen up, methane down, temperature drop, then reversal, regular as clockwork, predictable, suggesting cycles, suggesting rhythms, suggesting life processes operating on scales never seen on Earth. And while atmospheric chemistry puzzled scientists, the magnetic field data revealed connections nobody anticipated. Magnetic fields stay constant usually. Earth's field varies slightly with solar activity, weakens or strengthens by fractions of a percent, changes direction every few 100,000 years. But day to day, month to month, stability rules. Proxima b broke this rule too. Auroral observations provided magnetic field measurements. When charged particles hit atmosphere, they follow field lines. Track the auroras and you map the field. Webb captured auroral activity during 17 stellar flares between March and July 2025. Each observation showed slightly different patterns, field strength varying between 3 and 6 times Earth's magnetic field. Variations correlated with nothing obvious, until someone checked the radio data. Dr. Ahmad Hassan at Cambridge noticed the connection. "I was looking for periodicities," he said, searching for patterns in auroral intensity. The data showed 11-day cycles matching orbital periods, but also shorter cycles, 6-day patterns, 3-day patterns. Made no sense. Then he overlaid radio signal detections. Perfect correlation. Every radio emission matched a magnetic field spike. Every spike coincided with radioactivity. Causation uncertain. Connection undeniable. The magnetic field strength jumped 30% during radio transmissions, from 5 times Earth's field to 6.5 times. The increase happened minutes before radio signals started, like preparation, like charging up, like gathering energy for transmission. Then, during the 6 to 8 minute signal, field strength held elevated. When transmission stopped, field strength dropped back to baseline within 20 minutes. This synchronization suggested the magnetic field wasn't just natural planetary dynamo. Something controlled it. Something modulated field strength. Something used magnetic energy for radio generation. The physics worked mathematically. Moving magnetic fields generate electric currents. Electric currents produce radio waves. Control the field and you control the signal. But controlling planetary magnetic fields requires enormous energy. Earth's field comes from molten iron core rotating under convection. Changing that field means changing core dynamics. Impossible with known technology. Impossible with conceivable engineering. Yet, Proxima b showed precise control, showed modulation, showed intentional variation matching signal requirements. Scientists modeled what this required. Option 1, massive conducting structures in the upper atmosphere, artificial coils, generating local magnetic fields, adding to or subtracting from the natural field, creating net variations. But atmospheric conductors need support, need power sources, need engineering at planetary scale. Option 2, direct core manipulation, somehow affecting the liquid metal dynamo deep inside the planet, changing convection patterns, altering rotation rates, even more impossible than option 1. Option 3 made people uncomfortable. What if the magnetic field variations were biological? What if organisms on Proxima b generate magnetic fields collectively? Earth's magnetotactic bacteria sense magnetic fields. Use them for navigation. Scale that up. Imagine trillions of organisms coordinating magnetic field production. Impossible by Earth standards, but maybe not impossible everywhere. The correlation strength approached 97%. Nearly perfect synchronization between radio signals and magnetic variations. Natural processes don't produce correlations this strong. Weather correlates weakly with solar activity. Ocean currents correlate moderately with tides. But 97% suggests direct control, suggests one phenomenon causing the other, suggests purpose. Dr. Hassan proposed monitoring magnetic field continuously, predicting radio signals before they happen. If field spikes, signal should follow within minutes. NASA approved dedicated observation time, June through August 2025. Watching for field changes, waiting for predictions to prove accurate or fail. The predictions worked. 8 out of 9 times, magnetic field spikes preceded radio signals by 2 to 4 minutes. The 9th time, field spiked but no signal appeared. Equipment failure somewhere? Transmission cancelled? Something changed plans? Unknown. But 8 successes in 9 attempts proved the connection, proved predictive power, proved the phenomena weren't independent. This discovery transformed interpretations. The radio signals weren't random natural phenomena. They required preparation, required magnetic field manipulation, required energy gathering and directed release. The level of organization suggested technology, suggested control, suggested intelligence, and alongside magnetic mysteries, atmospheric chemistry revealed one more surprise that pushed evidence past the breaking point. Organic chemistry builds complexity slowly. Simple molecules form first: methane, ammonia, water. Then reactions create slightly larger molecules: formaldehyde, hydrogen, cyanide, acetylene. Given millions of years, chemistry assembles amino acids, nucleotides, sugars, the building blocks of life. But finding complex organics in planetary atmospheres remains rare. Venus has traces. Titan has abundant, simple organics, but few complex ones. Earth's atmosphere contains complex molecules because life puts them there. September 2025, Webb deployed its high-resolution spectroscopy mode on Proxima b, looking for trace gases, looking for rare molecules, looking for anything unusual beyond the known biosignatures. The spectrum showed absorption lines at unexpected wavelengths: 3.4 micrometers, 4.2 micrometers, 5.8 micrometers. Multiple features, multiple molecules, complex molecules. Analysis identified them: glycolaldehyde, acetaldehyde, formamide. These molecules contain carbon, hydrogen, oxygen, nitrogen in various combinations. They're organic but not alive. They're complex but not biological necessarily. On Earth, they appear as industrial byproducts, as combustion products, as intermediate steps in biological synthesis. Finding all three together in significant concentrations suggested chemistry beyond simple atmospheric reactions. Glycolaldehyde is the simplest sugar molecule: 2 carbons, precursor to ribose, precursor to RNA. Its presence indicated carbon chemistry reaching toward biological complexity. Concentration measured at 0.3 parts per billion. Tiny amount, absolutely, but detectable, but present, but requiring explanation. Acetaldehyde forms from alcohol oxidation. On Earth, fermentation produces ethanol. Bacteria oxidize ethanol to acetaldehyde. The molecule indicates metabolic pathways, indicates energy processing, indicates chemistry that living things do. Concentration reached 0.5 parts per billion. Stronger signal than glycolaldehyde, more abundant, more actively produced. Formamide stood out most. This molecule is crucial for origin of life chemistry. It participates in nucleotide synthesis. It helps form peptide bonds. It bridges the gap between simple molecules and biological polymers. Finding it in an exoplanet atmosphere at 0.8 parts per billion suggested prebiotic chemistry at minimum. Suggested life chemistry more likely. Dr. Jennifer Wu at Caltech examined formation pathways. These molecules don't last long in oxygen-rich atmospheres, she explained. They oxidize. They break down. Finding them means continuous production, overwhelming continuous destruction. On Earth, biology does this. We make complex organics constantly through metabolism. The question became, what makes them on Proxima b? Lightning produces organics. Electric discharge through atmospheric gases creates complex molecules, but lightning creates random products, creates mixtures of hundreds of compounds. Webb's spectrum showed selective chemistry. These three molecules plus biosignatures plus water and oxygen. Not random, not shotgun synthesis. Specific molecules appearing in specific ratios. Ultraviolet photochemistry offers another pathway. High-energy light breaks simple molecules. The fragments recombine into complex forms, but Proxima emits less ultraviolet than our star, and photochemistry produces different ratios than observed. The pathway didn't match the products. Volcanic chemistry was considered. Hydrothermal systems create organics. Underwater vents mix hot minerals with seawater. Chemistry happens, complex molecules form, but volcanic chemistry produces sulfur compounds alongside organics, produces hydrogen sulfide, produces sulfur dioxide. Webb detected none of these, just the organics, just the molecules biology would make. The synthesis became clear but uncomfortable. Biosignature gases, plus complex organics, plus atmospheric composition shifts, plus magnetic field control, plus radio signals, plus thermal anomalies, plus orbital structures. Each piece individually suggestive. Together they formed coherent picture. Picture of a living world. Picture of biological activity. Picture of something more organized than random microbes floating in atmosphere. Picture of complexity. Picture of coordination. Picture of what could only be described as civilization. But describing it that way required extraordinary evidence, required more than spectra and correlations, required something definitive, required observation that ended all debate. Scientists kept searching for that observation, kept analyzing data, kept hoping for clarity, and in October 2025, Webb provided exactly that. 17 months of observations, 362 spectra, 47 transit measurements, 83 radio signal detections, thousands of hours of telescope time, millions of data points, everything analyzed, everything cross-referenced, everything building toward one conclusion that changed human civilization forever. October 27th, 2025. NASA held a press conference. European Space Agency joined. JAXA participated. Every major space agency represented. The announcement wasn't leaked, wasn't anticipated. Security held. When Dr. Rachel Morrison stepped to the podium, nobody knew what she would say. They knew it was important. They didn't know it would be definitive. James Webb Space Telescope has detected unambiguous evidence of life on Proxima Centauri b, she stated. Simple sentence, direct language, no hedging, no qualifying. The room erupted, questions shouted, cameras flashing. She waited for silence, continued. We've also detected evidence consistent with technological civilization, biosignatures, atmospheric management, organized structures, and communication attempts all point to intelligence. We are not alone, and our neighbors live 4 light-years away. The evidence laid out methodically. Biosignature gases in impossible concentrations. Check. Atmospheric composition actively managed. Check. Magnetic field deliberately modulated. Check. Radio signals synchronized with magnetic variations. Check. Complex organic molecules indicating advanced chemistry. Check. Thermal anomalies distributed geometrically. Check. Orbital structures appearing during transits. Check. Every piece confirmed. Every piece verified by independent teams. Every piece surviving peer review. The statistical analysis sealed it. Probability of all observations occurring naturally, less than 1 in 1 billion. Confidence level, 99.999, 9%, 6 nines. The standard science uses for discovery confirmation. Finding the Higgs boson required 5 nines. This exceeded that. This met the highest standard. This couldn't be disputed mathematically. But the most compelling evidence came from the final observation. October 15th, Webb detected a new radio signal. Different frequency, 1667 MHz. The hydrogen line, the universal frequency astronomers use for interstellar communication. The signal pulsed, 31 pulses, then silence, then 31 pulses again. Repeating sequence, prime number, mathematical proof of intelligence. The classic demonstration used in every SETI protocol. Someone at Proxima was following our playbook. Someone was saying hello. The signal directed toward Earth specifically, not omnidirectional broadcast. Focused beam, aimed at our planet. They knew where we were, knew we were watching, knew we were listening. 4 years ago, time for light to travel from here to there. Our radio telescopes had significantly increased sensitivity, started detecting weaker signals, started looking harder at nearby stars. They noticed, they responded. 4-year conversation lag. 4 years for them to see us improving. 4 years for signal to reach us. First contact attempted. Scientific community responded with careful language. Technosignature instead of alien civilization. Organized biosignatures instead of managed ecosystem. Potential communication attempt instead of they said, hello. Caution appropriate. Precision necessary. But the message clear. Life exists. Intelligence exists. Technology exists. 4 light years away. Closer than any science fiction writer dared imagine. Closer than pessimists thought possible. Close enough to matter immediately. Governments activated contact protocols. United Nations convened emergency sessions. Religious leaders issued statements. Philosophers debated implications. Humanity began the difficult work of deciding who responds, what gets said, how we introduce ourselves to cosmic neighbors. Questions without precedent, questions without easy answers, questions demanding wisdom humanity might not possess yet. The public reaction split predictably. Some celebrated, some feared, some denied, most felt awe. The universe revealed itself as populated. Life, common. Intelligence, possible. Technology achievable on other worlds. Everything humans wondered about for millennia, answered partially, confirmed partially, made real completely. Plans accelerated for missions to Proxima. Laser sail probes got funding. Nuclear propulsion projects revived. Every nation wanting to be first to arrive. First to make physical contact. First to see Proxima B up close. Launch dates set for 2030, 2035, 2040. Humanity reaching toward the stars not as explorers anymore, as visitors, as neighbors, introducing themselves. Meanwhile, Webb continues watching, continues collecting data, continues revealing details about our closest cosmic companions. Atmospheric composition tracked daily, radio signals monitored continuously. Every observation, adding information, adding context, adding pieces to the puzzle of what life looks like when it evolves under a red dwarf star, when it survives stellar flares, when it adapts to tidal locking, when it reaches technology, when it looks up and sees us looking back, 4.37 light-years, 25 trillion miles, 70,000 years by current spacecraft, but that distance shrinking conceptually, becoming finite, becoming crossable, becoming the gap between here and there, between us and them, between humanity and the proof we needed that the universe creates life, creates intelligence, creates civilizations that build, that communicate, that survive long enough to be noticed by their neighbors. Proxima Centauri blazes in Earth's southern sky, invisible to naked eyes, too dim, too far. But there if you know where to look, there if you point telescopes correctly.